out real fast that it's very easy to set them up. All right. So if I wanted to, I want you guys to think back when you first learned how to graph stuff. When you first learned how to graph lines, what did you guys create to do that? That's slopes, but what did you do to find your ordered pairs? You plot points. You picked values of x. You substitute values of x in your function and generated your y value. Like Riser, where you were using slope-intercept form to figure out your x's and y's. We're going to do the exact same thing with this. But now we have to use our brains a little bit more to pick values that make sense. Okay? Now, I know it's a tough thing. I have high expectations. What can I say?
You give me 2 weeks without math, and now you want me to use my brain?
I know it sucks. But you can do it. I know you can do it. So, I'm going to ask you this one.
Just bursts into tears.
Remember, we're going to pick the values of x to substitute into the square root of x to generate some value of y. We're going to pick numbers that make sense. What's a very easy number to take a square root of? 1, 4, 0. Why am I choosing 0, 1, 4, and 9 for my values of x to take my square root? Because they're easy, because they're square roots. You can do them in your head. What's the square root of 0? What's the square root of 1? Square root of 4? 2. Square root of 9? 3. Okay. Now, notice in this case here, it's just saying square root of x. It doesn't say plus minus, it doesn't have anything in there. Okay. I'm going to explain that as we get into, there will be a time that the value here, it might say the -2 square root of x. That's going to change this ever so slightly, but for right now, it's still going to be patterned off the same basic principle. We want to take a square root of something that's easy to work with. Square root of 0, square root of 1, and so on. Right? From here, do you guys agree that my ordered pairs become 0, 0, 1, 1, 4, and 2, 9, and 3? Do you agree with that? Yeah. So you plot it. And your graph kind of looks like that. It's ever so increasing like that. Your square root functions are always going to look like that. I'd recommend make sure you guys do this without calculators. You're not going to get one. Okay? Not so scared? All right. What's your domain of that graph? Or that function, excuse me. Yes, x's are domains. So what are your domains? What's your domain here?
Like 0, 1, 4, 9.
Okay. Write it in generic terms then. What is your value? What are your domains for this function?
Numbers.
Yes, numbers. Domain is someone.
All real x's.
If it was all real, then I'd have negative value, wouldn't I?
Some real.
Bravo. Bravo.
Positive, all real. I'm not wrong, am I?
Rational?
No. Would I just say x is greater than or equal to 0?
Sure.
Stop overthinking it. It's all values of x that are greater than or equal to 0. What's your range?
All y is greater than or equal to 0.
Most people get that after we get the domain. It's all your y values that are greater than or equal to 0. Okay. Now, what's going to happen here is we're going to take this generic graph as well as the generic graph for the cube root, and we're going to start shifting them. Okay? But real fast, let's take a look at what this is. We haven't done this one yet. So let's do the same basic idea with the cube root of x. I'm going to do the same idea. I'm going to work with values of x that make sense. I want to take perfect cube roots. What are the perfect cubes?
0, 1, 8.
0, 1, 8. Yeah, it's going to take 0, 1, and 8. When I'm working with a cube root, can I take a cube root of a negative?
Yes.
Yeah. So I can use -1 and -8 as well. Now, you're right. You said 27. That's right. That's the next one in line. But it just starts to be too much. So when I'm using my cube roots, I'm generally going to pick 0, plus or minus 1, plus or minus 8, because those are cube roots that I can do in my head. All right? So I'm going to take the cube root of x to generate my y value. Cube root of 0, cube root of 1, cube root of 8, cube root of -1, and cube root of -8. What are those values? It's cube root of 0. See, you can't just give me ugh. All right, what's cube root of 1? Cube root of 8. Okay, cube root of -1. And cube root of -8. All right. Is that bad? Okay. I know you guys are all freaking out waiting for the other shoe to drop here. But wait. So at -8, -2, -1, 1, 0, 0, 1, 1, 8, and 2. So our cube root functions all kind of look like that. Okay. Kind of, it's like a reflected over. Now, in this case here, what's your domain?
All real.
All real. What's your range? All real. Yes, sir.
Does this have to do with, like, when you have x cubed, it's like the same thing, but high goes up instead of the side?
Kinda.
How do you do the all real numbers? Oh, yeah.
How do you do all real?
Yeah, how do you write the all real thing?
Oh, okay. The domain here
Oh, it makes it.
is all real. Guys, you can write all real. It's okay. It's all right. I'm saving lead.
Stop.
Collaborate and listen. Is every breath you take?
Stop. If you say in the name of love, I might get up and
I was trying to think of the lyric from Jane's Addiction. Stop. Jane's Addiction. No way. That's all right. So now
switching teachers.
I don't think there's one for that. Let's shift something. Let's do an AH. All right. Now, what we're going to do here with these is what we're talking about with these AHs and Ks. Your AH and K here is, again, when we had H's and K before, it was horizontal and vertical shift. H was horizontal, left and right. K was vertical, goes up and down for the Y.
We were shifting.
This is taking the whole math.
I did say all that.
Thing into account.
We're SMRT. So, I teach all the secrets of life the days you're absent. Oh. When we look at these things here, this value of A, what I want you to think of the value of A is kind of like, I'm going to go back to a little bit of slope. When your value of your slope was M, if it was the absolute value of M was bigger than 0, it was like very large, it was a very steep curve. If the absolute value was very small, it was a less steep curve. Do you agree?
Yeah.
No, think, just not smile, humor me a little. It's the same idea with the A values for the curves here, for square roots and cube roots. The A value have an absolute value that's very large. The curve is quicker, it increases faster. If it's low, it increases slowly. Same thing with the tails for your cube root. It's a real high curve or low curve. Yes. What? I know. Why are you laughing at me?
I'm laughing at him.
So let's walk through a problem. They're very similar in way they set up, And they're very easy to work with. So let's do this. Let's say it's y equals -2 square root of x plus 3 minus 4. Set it up this way. Now, sometimes you will see it written with the k value put out in front. Sometimes they do that by writing it as -4 minus 2 root x plus 3. Why do you think they do that? Yeah. So you don't put that. Yes, it doesn't get. You don't lump it underneath the radical. Okay. Sometimes you'll see it just written both ways. All right. What's your a value? -2. What's your h? -3. Good. And what's your k? Remember when you're working with h's and k's in this example, how it says x minus h? It means it's the opposite of the sign. The k value is whatever it is. Okay. So what we do here is we make 2 steps to graph this. Step 1. We're going to plot what's called a parent graph. A parent graph, or a parent function, is what we're going to model our shift off of. When you're working with square roots and cube roots, they tend to be very easy to do. You could probably jump right into the shift right off the bat, but I like to slow you down a little bit and put you into the parent function, because as we get into the more complex graphs that we'll do later, like starting second semester with logs and exponential growth and k, things like that, as well as trig, it's so important to be able to plot through a parent function first. It just makes your life so much easier. So we're going to plot the parent. Now, the parent function for these is going to look like this. Y equals a root x. So we're going to plot whatever that looks like. All right. You're taking out your shift. All right, taking out the shift, you're getting rid of the h and the k. But you're leaving the deal with the a value. So what we're going to do is we're going to plot y equals -2 root x. What are the values of x you think I'm going to choose? 0, 1, 4, and 9. So I'm going to pick values of x at 0, 1, 4, and 9. I'm going to substitute into that value, the square root of x, to generate my y value to get my ordered pairs. Okay? So what's -2 times the square root of 0? 0. What's -2 times the square root of 1? -2. -2 times the square root of 4? And then -2 times the square root of 9? -6. Good. Everybody okay with that? So now I know that I have ordered pairs. I have all of my ordered pairs now for the, oops, I'll put it here as my parent graph. We'll be at 0, 0, 1, -2, 4, -4, and then 9, -6. Plot it. Zero, 0, 1, -2, 4, -4, and 9, 6, 7, 8, 9, -6. And it's going to look like that. One rule when you're working with parent functions is that since you're using the parent function to model the shift off of it, what you want to do is you don't create that with a solid line. You put that as a dotted line, okay? Because it's a tool that you're using. It's not technically the right one. So you would just kind of do a dotted line to connect that. That's my parent function. The shift of this is step 2. And really all step 2 is shifting the points. By working with your parent function, that a root x in this case, we were able to come up with the 4 ordered pairs, 0, 0, 1, negative 2, 4, negative 4, and 9, negative 6. When we go back to the original problem, what was our shift? What was our h and k? Negative 3 and negative 4. So that means the x value, what am I doing to it? Am I adding or am I subtracting 3? What am I doing with the y value? Okay, so now my shifted ordered pairs would be x minus 3 and x minus 4, because that was my h and the k. So all I do to this is 0 minus 3. What is it? What's 0 minus 4? So it's at 0, negative 3, negative 4. 1 minus 3, negative 2 minus 4. And I'm going through that list to get my new set of ordered pairs. Does that make sense? But that's all you do for the secondary part there. You're taking the values that you've already figured out that your horizontal, your vertical shift from your h and your k, and you're moving the parent function those. So we're at, what would it? 1 minus 3 is negative 2. Negative 2 minus 4 is negative 6. 1, negative 8. 6, and negative 10. I apologize that my ordered pairs in the middle of my graph here, so I'm just going to move these out of the way real quick. Usually this, I did this earlier too. Usually I have this moved over a little bit more, so I apologize that my graph ran into it. Is that okay? So now when I go to plot those, I just plot my new points. Negative 3, negative 4. Negative 2, negative 6. 1, negative 8. 6, negative 10. 6 was 9. And it's been shifted. Okay? And it was shifted. We moved that graph to the left 3 and down 4 with that h and the k. So, yes, ma'am?
Will you be doing imaginary numbers?
No. There won't be any imaginary in this stuff, okay? Because, what's that? Why do we do what? No imaginary? Because that's what the problem is. The problem was to graph this, okay? The problem was to graph that equation to start out with, and that shift came from that h and the k. You start with that parent function, using very easy numbers to work with, get those ordered pairs, and add or subtract. Yes, sir?
Is the parent always y equals a square root x?
Yes, sir. Parent function is always going to be a root x. The parent function for the cube root is going to be always a cube root x, whatever it is. Okay? Then you go back and you go and do your shift. Now, let me ask you this. What's my domain and range? When you go to your domain and range, you always do that from the shift, not from the parent. What's your domain in this case?
All negative x is greater than greater or equal to negative 3.
Good. See why it's not all real? This has a stop. It's not a continuous function. All right? So by going into here, my domain is going to be x values that are greater than or equal to negative 3. Because if it was negative 4, I would have a negative. I would wind up with a negative root. Imaginary. It won't work. All right? My range. My range in this case, since my curve is decreasing, that means it's going to be all values of y that are less than, what was it, negative 4? Basically, your domain and range is going to occur where this shift winds up at. Yes, ma'am?
Wasn't it 2, negative 2?
Why is it at negative 2? Our shift function started at the negative. Yeah. It's basically going to always start at that first point. Whatever your origin got shifted to is going to be where your domain and range takes over from. It's just a matter of looking at the curve, whether or not it's be x is greater than or x is less than, or y is greater than or y is less than, depending on the direction. Right? So it's not that bad, is it?
Yeah.
What's the next part?
Yeah, there's always
The next part is just doing the same thing with the cube root function. The next part is the same thing with the cube root. You follow the exact same steps. So if I have your parent or your generic form was y equals a cube root of x minus h plus k. That was our generic form. We followed the exact same steps to solve these problems. None of that changes whatsoever. Move this over. So let's do this one. Y equals 3 cube root of x minus 2 plus 4. Making things up as we go. All right. What's my A, H, and K?
3, 2, and 4.
Good. We all right with that? A, H, and K is 3, 2, and 4? All right. So I can already see that I know that my shift is going to have a +2 and a +4 for the x and the y. You guys agree? So I'm just going to write that down. My shift, bless you. I know that's going to happen later on. Might as well write it down. You already know what's going to happen. Doesn't hurt any. Right? The reason I do that is because when we get to sine, cosine, I forgot what it's called.
Get lost in the effects.
Pay no attention to the man behind the curtain. Yeah, when you get to trig function stuff, it's so nice to label out what you're going to be doing, because when you start to make your scales, it just makes life easier. What's that?
Grab a triangle.
Not trying. No, you're going to graph this.
That's me. That's me.
Putting pi in there?
I quit.
We don't deal with degrees. In algebra 2, you don't deal with degrees. Everything's in radians.
Okay, let's go back.
I'm quitting school.
What's that thing? What's explain?
I'm gonna live under.
Hey guys, it's algebra 2. Algebra 2. All algebra 2 deals with trig. This is what everybody's going to do.
No, first semester you're just reading, second semester for each other.
No. So step 1. Oh. Maybe. I don't know. I love trig. I think there's so much cool stuff we do in trig. So step 1, we're going to plot out the parent function. Okay, I'm going to plot my parent function. My parent function here is my a cube root x. So it's going to be 3 cube root x. To get my ordered pairs. When I work with cube roots, is it okay that I have negative values?
Yeah.
So start at -8.
0 plus or minus 1 plus or minus 8.
Try not to get in the habit of writing +or -1, +or -8 in your when you do your table. That way you don't forget to do one of them. Because your answers aren't always going to be plus minus going the other way when you start worrying about shifts and stuff. Okay.
All right.
So we just go through it, and like I said, it's not a. We're trying to do this as basic as you can to be able to do the mental math here. All right. Some simple cube roots. So you have the cube root -8, 3 times the cube root of -1, 3 times the cube root of 0, and 3 times the cube root of 1, 3 times the cube root of 8. Well, it's cube root of -8 times 3. -6. I think you get -3. 0. In this case, you get 3. 6. Right. For this parent function, that gets me on my ordered pairs for the whatever that's going to look like when it's increasing or decreasing. So we plot it. So our parent and we get this. You all right with that? Like I said, relatively straightforward. It's not a lot of crazy here. All right. Step 2 then is just taking those ordered pairs and adding the h and the k to it. Adding or subtracting depending upon what h and k winds up being. All right. So I'll change color. So -8 plus 2, -6 plus 4. Yes, sir.
Can you just go straight to the actual thing, or do you have to do the parent?
Like I said, the reason I'm having you guys do the parent one really is getting you ready for when we do stuff like this. Because if you can do the parent stuff now, and I know it is painstakingly simple to set a lot of these up. When we get into the more complex ones, you're going to be happy that you remember how to set the parent, because you're thinking about ordered pairs. They're going to be very easy to work with. I mean, when you get into something like this, you don't want to jump right to it because it's all out of whack. Because you're going to have asymptotes, you have all this other stuff going on. It's trust me. What are you whining about?
Oh, I said everything comes back full circle. Get it? Circle.
Radiance, I see what you...
That's actually
Roundabout circle, circle back around.
Very good.
Thank you.
Another song.
Why songs?
Why not? All right, so we shift out our points.
This isn't math.
Is shifting stuff.
Yeah. Shifting is step 2. It's basically adding. Yep, it doesn't change. It doesn't change with these. -1 and 2 is 1. -3 and 4 is 1. 2 and 4.
Such a problem. Such a
3 and 7.
10 and 10.
10, yeah. So that's what happens when you start listing them out. You get all your ordered pairs, and you just go ahead and replot those on the graph. Some people take the parent function, and they will take each individual point and rewalk them through on the graph. I don't like to do that a lot of times. I think it tends to get pretty messy on some of them. I think it's easier just to add them in this way. So it's just a matter of replotting. 4, 6, and 2, 1 and 1. That's a Hall Notes. The passion.
Then why are you singing?
Because they were poppy and tuned, and they made a lot of money, and it's annoying. I can only think of stupid things I would do rich. Okay?
I didn't think sideways.
Now, what's your domain range for this case?
Something involving
Domain. X is greater or equal to negative.
All real numbers?
Isn't that a continuous function? Is there anything that x can't be?
fair enough.
Just like you guys.
We don't judge.
You can be anything you want to be.
Thanks, Mickey Mouse. So is that
I want to be not in this class right now.
And these cube functions is generally going to be all real for both of them. You don't have to worry about it.
Let's make that stupid.
Explain one more time how I know the difference between like all real numbers or if it has a stop in point.
Okay. See how in this graph, it's continuous between negatives and positives. There isn't a value that it doesn't work. There is no number that I can't take the cube root of. I can take cube roots of negatives, I can take cube roots of positives. Do you agree? Whereas when I'm looking at a square root value, if I look at this here, x plus 3, if I choose any number that is smaller than -3, it won't work because then I have imaginary. So it means all my values have to be greater than -3. And your k value is just basically telling it's going to be everything above.
There's nothing.
Oh, this is below because it's negative.
There's nothing that goes to quadrant 4. How do we? Can you go back to the graph?
Of this one? Of the square root?
Of the one we just did.
Oh, yeah, yeah.
There's no free quadrant, the bottom right one. How do we have numbers there?
Because the values of x are positive for y then. That's all. Remember, x generates the y. That's how you're getting your domain. Your domain generates your range. Your domain being a positive value of x just so happens it creates a positive value of y. It doesn't have to land in every quadrant. All right? It doesn't have to land in every quadrant. That would be a mess. You want to try one on your own?
No.
Yeah.
Good. Do this one.
These are no.
Fractional. You guys are fractional. Thank you. These are too easy. We did. Oh, wrong one.
I feel like Emma has a lot of years surrounding this class. Just like Andrew and me. It's like in those commercials for depression. Or like those ones where they fall in like a pit, like that is out too.
All right.
Oh, thanks for the practice.
I want to walk you through. Yeah, square roots you're gonna have restriction. Cube roots you're gonna have basically all real. All right. Let me show you a little trick here with the fractional a value. No. Now, you guys agree that your first step is to plot the a square root of x in this case, right? Okay. Now, remember, you're doing this without a calculator, so you want to pick values that are easy to work with. So if I'm going to plot out y equals 1/2 square root of x, what are the numbers of x I'm going to choose?
0.
0. I'm going to use 0, okay.
2.
4.
16.
16.
36.
Why am I choosing those numbers?
They have even halves, not even halves.
Because when you take the square roots of them, they become even, so it's easier to plot. You're thinking ahead of the curve. Bad pun on that part. I wasn't trying to be punny on that.
Wow.
It was okay.
You could have just
All
like
of us.
I know, but I caught it, and I knew somebody would have gone, boo. So,
That's something Leo does.
now, this does happen from time to time. They're going to throw a fractional a value out at you that you have to stop to think of, all right, what are going to be the roots that are going to make my life a little bit easier? Does it matter that your things aren't drawn to scale? No. It still works the same. Okay? So I take the 1/2 square root of x to generate my y. So I still get 0. What's half of the square root of 4?
1.
Thank you. So what's half the square root of 16? 2. What's half the square root of 36? Okay, see how it's all, you're using numbers that make your life easy. Make sense?
Numbers. It's going to take
What's
a lot
that?
more than
No, because you can just budget.
that. That's the science mentor.
It is. There's 0, 0. 4 and 1. Here's 16 and 2. Here's 36 and 3. Because you're telling me what the ordered pairs are. You're telling me what my ordered pairs are. There's no reason for you to mark it off and take marks. That's just silly. Okay. It just so happens that your curve is going to be, this would be, if you did plot it out long form, your increasing square root would just be ever so slight. That's all. It's not as steep as an a value of 4. Okay. Does that make sense? And then it's just a matter of plotting out and your shift points off of that. It is not a difficult thing to process through, but think before you start putting in the same values each and every time. You're not all, I mean, a lot of times you're going to be using, that 0, 4, 9, 16. But sometimes 9's not going to be helpful. 1's not going to be helpful because you've got the different fraction. Same thing with cube roots. Think outside of different cube roots, you know. What's 5 cubed? 125. God bless you. What's 4 cubed? 64. What's 6 cubed?
256.
I think it's 216. 252. I think it's 216. What's 10 cubed?
A lot.
1,000. Okay. It's little things like that that you try to think of. What can I do to make my life easier besides walking out the door?
Will the highest radicals that will be?
Yeah, we're only doing squares and cubes. I'm not doing any others. We could. It's not that. The process is exactly the same. You're just going to pick numbers that you that deem easy. You know, if I'm doing the 5th group, I pick out 36. We get the idea where it goes. All right. Let me give you some of these to try. Make sure when you're doing these guys, make sure you list out, just like we did in our notes in class there, list out your parent function points and then list out your shifted ones when you're drawing them out, okay? If you want to use graph paper, if it helps you visualize a little bit better, I've got plenty of it lying around here somewhere. It's really not that bad, but you'll have to do, I mean, obviously you're not going to fit it all in one spot. So. And no, not today.
No, I would like my life. It's too late.
I feel like it's awful. It's awful. It's too far away.
Oh no!